Ma'am, we are live.
Okay. Hello, everyone. Welcome today. It's a special day. 23rd June is Women in Engineering Day. And it's a great way for us to celebrate the journey of women into the field of engineering. So to celebrate today, especially, we have with us a special guest, Dr. Manasadevi Thirugnanasambandam. She is the R&D Scientific and Technical Officer at IUCAA, Pune. She will be talking today about gravitational waves. She will be talking about the advanced technologies spearheading the search for gravitational waves. I'm sure you've all heard about gravitational waves, but what were the challenges in creating the instrumentation to detect to such level of sensitivity? I hope our speaker will address that today with us. Dr. Thirugnanasambandam received her PhD in physics from the University of Electrocommunications, Tokyo, for her research work in solid-state laser cavity dynamics. She then moved to Caltech, California Institute of Technology in the US for her postdoctoral research, where she joined the LIGO, which is Laser Interferometer Gravitational Wave Observatory Instrument Science Group. She also spent her postdoctoral research time at Kansas State University in the US, working on optical meteorology and sensing before moving back to India in 2018 to join the LIGO India project team at IUCAA, Pune. She has been a member of the LIGO Scientific Collaboration for over 10 years and is a contributing author to the work that established LIGO's first detection of gravitational waves, which, as you all may know, won the Nobel Prize in 2017. She's currently involved in the installation activities of the LIGO gravitational wave detector that is now being built in India. It's called the LIGO India Mega Project. Her current research lies in quantum-enhanced optical precision measurements, which will significantly improve the sensitivity of instruments used in multiple technology domains. So as we can see, she has worked with, the sensitive instrumentation that LIGO has needed. Welcome, Doctor. Welcome you today. And I invite you to please share with the students what has been your journey as a woman engineer or a woman scientist. How have you made your way here into one of the most famous and notable projects in the country in astronomy right now?
Thank you, Dr. Mitra. Can I share my slides?
Yeah. Yeah.
Okay.
We can see it.
Hello, everyone. Thank you for the kind introduction, Dr. Mitra. I'm very happy to join you, everyone, on the special occasion of International Women in Engineering Day today. And it's very important that we recognize these occasions in order to raise awareness, to increase the diversity of women in STEM and engineering. The theme of this year, I'm told, is Together We Engineer, which is in the spirit of collaborations, working with collaborations among engineers. And I think the project that I work on is a very apt example of how an international collaboration of engineers and scientists come together to make breakthrough in science. So today I'll talk a little bit about myself as to how I landed up here, and then we will discuss about the actual technology which I'm interested in, and the one that actually motivated me and still motivates me to keep going in the stream of research. I am um, by training, I'm a physicist. So I did my BSc and MSc in physics. And then I went on to do my PhD in experimental physics. And I worked building lasers, and my expertise is in optics and coherent sources. And from there, I moved on to join the instrument science group at Caltech, which works on which works towards building the detector for detecting gravitational waves, that is LIGO. And then I honed my skills into precision measurement, and now I'm with the LIGO India project since 2018. So by affiliation, people call me a scientist, but I like to call myself an experimental physicist. And the reason behind this is because apart from exploring fundamental physics beyond, we go beyond and push the technology to make it applicable and fruitful and be able to see the outcome of it. And I think that's what an engineer does. So an experimental physicist is somewhere in the overlap between a scientist and an engineer in that sense. What I do today, I work with the LIGO India project. For people who are not aware of what LIGO is a large interferometer. It is an L-shaped detector, which is 4 kilometer in one side and 4 kilometer on the other side. And the detector is being built in India to detect gravitational waves. There are many other detectors which form a network around the globe so that we are able to detect gravitational waves from different sources across the universe. LIGO was one of the ambitious projects taken by NSF in the USA a few decades back. And it's an ambitious project taken up by India to have such a detector on our soil. So LIGO India will be the next much expected detector that will go online in the next few years. So then I'll talk a little bit about what I work on to understand what we really work on. What are the technology aspects, that we work on? I would like to give you some introduction into what gravitational waves are, and how people went about trying to detect these gravitational waves, and why it took people so many decades until we had the first detection in 2015. This year is also special for us because it marks the 10th year anniversary of the first detection of gravitational waves. So you will see several events happening throughout the year, especially on September 15th, when we had the first detection. So there are several events being planned across the collaboration in different countries to commemorate this special occasion. Then I'll talk about the LIGO technology that has pushed the limits of instrument science over multiple decades, and where we are heading to also, because the road is long. We just opened up a new field. So the road is long, and there are several questions to be answered. So everybody, I'm sure, knows the fundamental force of the universe, gravity. And according to Newton described gravity as a force. And his description only talks about the effect of gravity. So when there are two masses, they attract each other. It talks about the force and describes the force. But how this happens about, the way in which gravity acts, was described by Einstein as gravity being a curvature of space-time, and that curvature is what results in the fundamental force of the universe. And when these masses move around in the fabric of space-time, they create twists and ripples in the space-time fabric. Um, so if you consider a very heavy object that has a very high density, for example, a star, a heavy star, then the star warps the fabric of space-time around it that creates kind of a stretch in the space-time. And but when this particular mass is in motion, what happens is it tries to drag the space-time curvature along with it. And that brings about the motion of the mass, the motion of space-time curvature itself. And now, if you were to imagine two such masses moving dynamically in space, what happens is that the motion gives rise to space-time ripples, as you can see in this picture. And this is what we call gravitational waves. And what we are trying to do is detect these gravitational waves because they have the astrophysical information of the massive objects that are in motion, as well as the result of these masses combining together and giving and forming a final black hole as well. So um, so we told that these are waves, right? So everybody must know what are electromagnetic waves. So this is the light we see and the light that we don't see. It comes from radio waves all the way up to gamma rays, and light also have what we call a wavelength. And you can see it has a wavelength and it has a frequency as well. And when we are looking at the universe, we also observe the objects in the different parts of this electromagnetic wave spectrum. Which means that if I'm going to look in the visible region, I have a telescope that is sensitive to only the light in the visible region. And if I have a gamma ray telescope, I'm sensitive to the emissions only in the gamma ray wavelengths. So similar to this, the gravitational waves also has a spectrum, and they have a wave period, which is the wavelength, as well as frequency. And depending upon the sources that emit these gravitational waves, the wavelength and the frequency of the gravitational wave that we detect is also going to be different. So now we've said that gravitational wave is a wave, it has its wavelength, it has a frequency. So how do we detect a gravitational wave? When we consider an electromagnetic wave, for example, you listen to your AM radio and FM radio. We have AM radio and FM radio waves all around us. But until you have a radio that you can tune to the particular frequency of your FM or AM, you cannot actually listen to the broadcast. So, in the same way, if you want to listen to a gravitational wave, you need to build an instrument that is capable of picking up these signals at the particular wavelength of frequencies. So, for building such an instrument, it's important to know what is a physical effect of a gravitational wave. If I have an object, what does the gravitational wave do to the object? So for this, what we consider a ring of freely falling test masses that are not subject to any other force. So, and if there is a gravitational wave that's going to pass through this ring, what the gravitational wave does, it stretches and squeezes the ring like you see in the picture. And a whole gravitational wave oscillation, a wave, looks like this, what you see in this picture. And the stretch and squeeze can be plus plus with orthogonal direction as well as cross cross. And you can see the warp is different in these two pictures. So we call electromagnetic waves as bipolar. And in this case, because of the stretch and squeeze effect in 3 dimension, these gravitational waves are what we call quadrupolar waves. So if you have to look into the stretch and squeeze effect, I'm not able to play the video. So the stretch and squeeze effect in the gravitational wave will will give rise in a ring will give rise to the stretching and squeezing effect of the free mass. Now, if you were to consider the stretch and squeeze, so we are all surrounded by gravitational waves. Now, if you were to consider the gravitational wave passing through us, we would also be stretched and squeezed. And this video shows exactly how the stretch and squeeze effect actually happens. It's much, much exaggerated from what you think. So in LIGO, what we do is we use an instrument that looks something like the L-shaped detector, and it's stretched and squeezed in orthogonal directions. So now you see a bunch of people sitting, and if we have a gravitational wave going through the frame of the people that you see the stretch and squeeze effect that happens. But this is way, way exaggerated. So when people wanted to detect gravitational waves, they wanted to build different types of detectors. The first detectors that were proposed were what you call the bar detectors, as you can see in this picture. So you have a stretch and squeeze effect from the gravitational waves. So if you had a bar and if you were to be able to measure the stretch and squeeze and make it ring and amplify that particular stretch and squeeze, you should be able to detect gravitational waves. But this was very, very hard because it was difficult to isolate the bar detector from all the noise that is surrounding the detector itself. The next famous proposal came to build Michelson interferometers, and the one of the first prototypes you can see, this is the prototype at Caltech. This prototype still exists because it gets upgraded with the detector itself. And this was a prototype that was built to prove the proof of principle before the LIGO project was launched. Right now, with many more decades, the Michelson interferometer is proved as one of the best options to detect gravitational wave detectors, and there are multiple network of detectors that are there spread across the globe in different continents. So when I say how we use interferometer for gravitational wave detection, the way we use interferometers for gravitational wave detection is when you consider a wave, the wave has its own wavelength and frequency. Now, what we do is we trying to play the video again. Yeah. So when we have two light waves,
Do I need to share the sound or you have?
no, sound, I think most of them are just visuals. I have sound only on one slide.
Okay. Okay.
So when we have light waves that go in two different directions, and when they come back, and if they combine peak to peak or trough to trough, then they produce constructive interference, which means you'll see a brighter spot. But if they interfere peak to trough, then you will see a dark spot. And that is exactly what happens in a Michelson interferometer. Depending upon the position or the stretch and squeeze of the arm, the length that is traveled by the light across these two orthogonal directions will be different. And this stretch and squeeze effect will give rise to a change in the brightness of the spot that you see in the recombined light. So how much of a change are we talking about? I mentioned that the arms of the LIGO interferometer are 4 kilometers. So we are trying to measure a displacement of roughly 10 to the minus 19 meters across 4 kilometers. This means that if you consider the distance between the sun and the closest star to the the sun, which is the Proxima Centauri, and that's four and a quarter light years roughly. We are trying to measure the width of the hair across a distance between the sun and its closest star. So that is the precision of motion, of the stretch and squeeze that we are trying to measure. And this is the reason why we don't feel gravitational waves just passing through us, because you should have something that is sensitive enough to be able to to measure the distance, the change in the length to down to 10 minus 19 meters. And that's very, very challenging. And for a very long time, people believed it's not going to be possible until lasers came through and the birth of LIGO happened. So as you can see, this is the proposal that was put together for building LIGO back in the 1980s, early 90s. And you can see here, there is a laser, and then there is the same beam splitter that actually reflects the light in two orthogonal directions. And the light comes back and then it recombines. And that's where you record the signal. So there were many people who played the key role in that. The well-deserved Nobel Prize of 2017 went to Rainer Weiss, Kip Thorne, and Barry Barish. It is not easy to pull up such a big project together because, as you can see, cost-wise also it is a mega project and it requires a community to come together to pitch for the science impact of the detector, and also the plausibility of being able to showcase the technology that will be relevant to build this detector and make a detection. So if we look at the timeline of gravitational waves, as I said, the bar detectors were the first, and that happened somewhere in 1970. And around the 1980s to early 1990s, that's when the interferometer-based detectors started picking up fame. And then by 2000, we had the first kilometer scale detectors in several places across the globe. And from then on, people have worked for almost 2 decades before they had the first detection in 2015. And now we are heading to the third generation of detectors as well, which are all in the proposal stage at the moment. So which are the detectors?
I'll just request you to explain that, the interferometry part once more, because some kids are just asking you to repeat it once more. Yeah.
So in this picture, what we have is a Michelson interferometer. So what we have here is the laser in here. And what happens is we have a beam splitter here. So the laser light hits on the beam splitter and it is divided into two equal parts. So one travels along, say, the X direction, and the other light travels along the Y direction. And we have highly reflective mirrors at both the ends. And the light reflects back and reaches the beam splitter again, and they recombine. And the recombined light comes back at the orthogonal port again. And that is what we call the dark port of the interferometer. So now if the light that comes back it combines with peak to peak of both the waves, then we have what you see is a bright spot. As you can see here, this wave pattern shows this is the combined light. So when they meet peak to peak, like as in now, you see a enhancement. But when they meet peak to trough, you have zero. That is a destructive interference. So you have constructive as well as destructive interference. Now, when I lock my interferometer, or which means when I hold the interferometer at, say, a dark spot, and now a gravitational wave comes by, what the gravitational wave does is it stretches and squeezes, right? So one of the arms of this Michelson interferometer gets stretched and the other one gets squeezed, which means if you had aligned them peak to peak or peak to trough, this alignment no more exists. And now you're seeing a change in the brightness of the spot in the recombined light because of the stretch and squeeze effect of the gravitational wave in the Michelson interferometer. And this is the basic principle of gravitational wave detectors that use interferometry. I hope that's clear. I can come back to it if you have other questions based on this. So now what we have is these are all terrestrial gravitational wave detectors, means they're based on in the Earth. And they're all interferometric gravitational wave detectors. So we have two detectors in the US, one located at Hanford, Washington, and the other one is LIGO Livingston. And we have Virgo, which is a 3 kilometer. I said LIGO is a 4 kilometer detector, and Virgo is a 3 kilometer detector, and that's located in Italy. And we have Kagra, which is a 3 kilometer detector in Japan as well. And this is a recent combination, a recent addition to the network of detectors. And we expect LIGO India to join this network with a 4 kilometer Michelson interferometer in the next few years. We also have certain proposed detectors. There is the cosmic, these are called the third generation of detectors. We have the Cosmic Explorer, which will have 40 kilometer arms instead of 4 kilometers. It's pretty difficult. I can tell you what will be the difficulties of actually extending the length of the arms. But the sensitivity of these detectors is directly dependent on the length of the arms. So the longer I have, the more sensitive my detector is. So people are interested in having longer and longer arms. And then we have the Einstein telescope, which is built again in Europe. It will be a 10 kilometer detector. And it's going to be a little different. It's not going to be the L-shaped, it's going to be a triangular configuration. So as I showed you, so I've showed you the basic structure of what the detector looks like. The detector actually has a laser and it has mirrors, and we're going to detect the motion of these mirrors at a readout. So the components of the detector are obviously optics, mechanics, and electronics. And in the heart of it comes interferometer control. You should be able to hold the interferometer at either the constructive or destructive interference, and then allow it to observe for gravitational waves so that you can see the shift in the brightness of the recombined spot. So that is what we call interferometer control. So it's not an easy task. As you can see, there are several components, and it's a very, very challenging task because of the precision levels that are involved in here. And that is why LIGO collaboration needed more than 1,000 members across multiple countries, and it has taken us more than 4 decades to get to the first detection. So LIGO did not get built in a day, right? So I told the first version of the kilometer detectors happened sometime in the in the late 1990s to the early 2000s. And the first generation of LIGO, as we call initial LIGO, the facility was built and the observation runs started, as we call the science runs, means the detector is observing for gravitational waves. It started in 2001. And in this plot here, what you see is the x-axis is the frequency, which is the frequency of the gravitational wave that you want to detect. And the y-axis shows the displacement, or that is the borderline zero of my detector, which means that any displacement which is greater, which is bigger than this particular line at the particular frequency is what will get detected. So as you can see, from 2001, the levels have gone down from 10 minus 13 all the way till 10 minus 19 in September 2006. So we did reach 10 to the minus 19, but then it has taken so many years and the technology advanced, and people said they didn't get any detections until 2006 with the initial version of LIGO. So they said, oh, we have advanced technology. Now we can push the limits of our detector in every aspect, because the lasers that they used in 2001, we had better lasers by then. We had better ways of having well-polished mirrors, and we had better ways of controlling them. So in 2006, the observation run stopped, and then the next generation of gravitational wave detectors was built. And As you can see in this picture, this is what a current gravitational wave detector would look like. It's a cartoonish picture, but it does have all the details. So what you can see is we have the laser in here, and the laser has to be very stable, right? If the laser is going, you're going to look at the brightness, the change in the brightness of the spot. And if your laser is not good enough, the change in the brightness can come from the laser itself. So the laser has to be a very stable laser. So the laser undergoes some sort of filtering and some sort of stabilization so that it is very stable and a very coherent source. And from there, you have this beam splitter in here that divides it into two directions, two orthogonal directions. And we have 4 kilometer arms on both sides. So these are 4 kilometer arms. So as I said before, that if the length of my arm is long, then my instrument is going to be more sensitive. So a clever idea came up. So what they did was they put another partially reflecting mirror in the arm cavity and made the light in here bounce multiple times across the 4 kilometers before they come to recombine at the beam splitter. Which means if I make them bounce back 100 times, my light has traveled 400 kilometers instead of 4 kilometers before it recombines. So the effective length of my Michelson arms have become 400 kilometers now. And that's very clever, right? So the simple Michelson has come into a gravitational wave detector, which is what we call a modified Michelson interferometer. And then we have the readout electronics, which actually get the data. And then there is a bunch of analysis that goes on to calibrate the data and be given to people who do astrophysics. And inside the detector, we also, so these mirrors that I told you are also are the ones that are going to be subject to the motion of the gravitational motion from the gravitational wave. And as I said earlier, the object for it to move, it should be a freely falling test mass, which means it should not be subject to any other force around it except for the gravitational wave, which means it has to be quiet for everything else around it. If you walk around it, the mirror should not move. But when a gravitational wave comes by, the mirror should be able to sense its motion. And to achieve that, the mirrors are actually suspended and isolated from the surroundings, from the vibrations around the surroundings as well. So there's a lot of technology that goes into building this. And that's the reason why it pushes the technology to its limits even to this day. So we talked about initial LIGO, and initial LIGO's target was somewhere 10 minus 19. In here, the y-axis is not in the actual displacement, but in strain. So there is a order of 1,000 different in the numbers that you see. So advanced LIGO brought it down to 10 minus 24 or 10 minus 21 if you look in terms of displacement. There are different noise sources that come into the instrument. For example, you should be able to sense everything that moves the mirror and be able to remove it from the mirror before it reaches the mirror. So that's quite challenging. So I'll talk about the key technology that makes this possible. One thing is the laser itself. This is one of the quietest laser in the whole world. And this was built by our collaborators in Germany. As you can see, this is actually roughly a 5-meter long table, the laser itself, and it operates at room temperature, and it gives out a whopping 180 watt. And the first initial stage of LIGO operated at 10 watt. And you can see when we did the upgrade, you can see the level the technology has pushed it. So we were able to make the light source jump from 10 watt to 180 watt. And you get a 10-time improvement in terms of the stability of this laser as well. So which means that you're able to push the sensitivity of the instrument right from the laser itself. Then the mirrors. The mirrors are the key components of the detector because they are the ones that are going to sense the movement of the gravitational wave. And these mirrors are roughly 40 kilograms, and you can see a person working right next to it. What she's doing here, she's coating the surface of the mirror so that it is so that to prevent dust particles and keep it protected, the surface protected. And in here, the instrument that you see, this is called the LIGO. The mirror is mounted. And what they do is they check for the abnormalities or the flatness of the surface. And the flatness of the surface has to be of the order of nanometers in terms of the flatness, which means the difference between the highest point and the lowest point of the mirror should be of the order of 10 nanometers, tens of nanometers. And the size of the mirror is about 35 centimeters. So it's quite huge. It is not a one-person job to lift the mirror either. Uh, and the mirror is very careful. You can see there are always multiple people working together because it's a really difficult job and it's a really precise job also. So, so the mirrors are what we call large super mirrors. The only person who makes it for LIGO is, LIGO is the only vendor for such mirrors. Because nowhere else they use such large super mirrors in any other project. And these mirrors, as I said, in order to be isolated from the different vibrations around it, other than the gravitational wave, they have to be mounted in what we call suspensions. It's like a pendulum. So it's a pendulum that is suspended from a high point, and there are 4 stages to this pendulum. And the way this mirror is suspended is by using glass fibers. What you see in the picture here is actually how these glass fibers are drawn. You can see there is some shining light that shows you where the fiber is. So there are 4 glass fibers that are soldered to the test masses or the actual mirrors that are going to sense the motion of the gravitational wave. And this itself is an engineering feat. It's a 40-kilogram mirror, and it has to be suspended on 4 glass fibers without any breakage and be able to move freely when a gravitational wave falls on it. Then comes the another key system that pushed the technologies in advanced LIGO is what we call the vibration isolation system. So all the optics that you see in the interferometer are mounted on a table or from a seismic isolated platform, as we call it. These blue things that you see, they are the external platforms. And then you have the internal platforms that actually hold the optical tables as well. So in here, you can see how such a assembled seismic isolation system is actually put into the chamber. And you can see the size of the people just standing nearby. So there are huge cranes that bring the assembled seismic isolation stages into the vacuum chambers. So this has multiple seismometers that detect the seismic waves. There are multiple sensors and actuators that actively sense as well as actuate in the negative direction before it impacts the actual mirrors that are there on the table itself. So the vibration isolation is something that's very, very crucial for LIGO. Next comes the controls and data acquisition system. So I said there are these 2 mirrors that are there in the L-shaped detector, and the entire detector is in vacuum. Means all the mirrors, the light goes inside vacuum, and the rest of the interferometer is all inside vacuum, which means there are 2 tubes, and inside the tube there is a vacuum that's created. and the mirrors are all closed. So there's no way for that. That's to avoid the disturbance of the air currents that are around us, as well as the different particles that scatter the light and give rise to noise. So you should be able to move these mirrors and actuate on them and be able to give them signals to keep them stable. So that happens all remotely. So this is one of the data centers which is the heart that that gets the data. And the way we control the detector is at the control room. So all we are able to do is there are analog controls as well as digital controls. And everything is done remotely. So when we are in observation mode, there's nobody near the interferometer, and everything is done remotely from what we call a control room. Looking at the light that leaks from different parts of the interferometer, we have viewports that collect the light, and we get signals from the different detectors, and that's how we sense what is happening inside the vacuum. And everything is possible by sitting in the control room, and we can remotely control and acquire data from the detector. So what the detector actually looks like. So in here, the first picture, what you see is what we call the central station, mid station as we call it. So in here, what you have, this is the beam splitter. This is where the beam splitter is hosted. And then you have two arms that run along from here over 4 kilometers. The picture here is actually a picture inside the beam tube. There is a beam tube. This beam tube runs for 4 kilometers. There is cement shielding. And this is what it looks like inside the beam tube. You can see there's a person actually putting baffles to control the scattering of light. So it can conveniently fit uh, a person inside the beam tube. What you see here is again a person standing next to one of our tall chambers. Um, so all this technology eventually led us to have our first detection that happened in 2015. So this is a video of uh, for the signal that we received from the first detection. As you can see, if you look at the frequency of the gravitational waves that we detect, they fall in the audible wavelength, which means that we are audible frequency. So we are able to hear these signals as well. So what you see in here, you will see that comes at the end. And that's the actual gravitational wave signal that you're looking for in the stream of data. I'll play that one more time. You'll be able to hear the that happens. And that's the gravitational wave signal that we detected. And this signal actually came 1.4 billion light years away. And we heard two black holes collide and make a detection at the interferometer. It moved the mirrors of the interferometer so that we were able to make a detection. So where we are now, we've come a long way from 2015. We've had 4 observing runs from 2015 onwards, and now we are in 2025. We are in the 4th observing run. We recently just started after the second break of the 4th observing run. We've had more than 200 detections as of now. What you see here is only till the data until the 3rd observation run, which is roughly, we had 90 detections that happened up to O3, which is the 3rd observing run. And we've had so far in the 4th observation run nearly 200 detections already. So moving forward, where we are moving towards, so LIGO, so as I said, these detectors are all over the world, they're distributed. And for you to be able to exactly look at the source as to where these are coming from in the sky, you definitely need more than one detector. So the gravitational wave community as a community thrives from having an international network because it gives better localization, or means position of these sources in the sky when you have more than one detector. And LIGO India uh, will make a very significant impact in trying to localize these sources, because as you could see, the existing detectors are all far higher up in the northern hemisphere of the earth, right? So the one that is closest to the southern hemisphere will be LIGO India, and that will increase the localization. Means if you will be able to tell a particular source within a less error on the sky, in the volume in the sky, much easily when LIGO India joins the network. So this effort started in the early 2010, 2011, and a consortium was formed. And then they met several times, and a proposal was given to the government of India, which received an in-principle approval in 2015. So the consortium then became the project, the LIGO India project. The LIGO India project will come up at Hingoli in Maharashtra. And we had the actual inauguration of the project that happened in May 2023. So now we are in project mode, and we're all working towards installing the LIGO India detector in India. There are several activities that actively go on in IUCAA, as well as all in different member institutes. We organize workshops for students from undergraduate levels. We also have meetings between different research groups all over India as well. So it's a very active, now we are actively pursuing, because we are in project mode, and the awareness is important because this is the detector for tomorrow. So we want to attract as many young talents as possible and sensitize them about how much of a daunting task it is to build a detector, and our detector will stay for another few decades, and we want the next generation of scientists and engineers to be motivated to come and contribute and establish gravitational wave astronomy. um, so not all action happens at the observatories that you saw. Uh, there is a lot of test and trials that run before that. And those happen in small labs with students who dedicate hours and some months and years working on improving and pushing technologies. So the students you see here, most of them are engineers. We students who come from physics background, as well as students who do mechanical engineering, who do electrical engineering, who do computer engineering. So all of them come together, and because LIGO is a project that is very interdisciplinary, so it is attractive for students from different streams of engineering. It's not biased to people from any one stream. So I welcome you all if you're motivated to do astronomy, as well as you have a footstep on the other side wanting to do engineering, to come and visit us if possible. We will have many, we do have multiple outreach programs. We have booths that are set up in colleges every time when there is a college fest. So, and you're always open to come. We have open house every year at IUCAA. So you're most welcome to visit us anytime. I can take questions.
Yeah, thank you for that presentation. It was, very different from what the students have heard of before, because mostly they've heard of telescopes in the electromagnetic waves range. So they had a lot of questions. So I'll bring forth a few of them to you.
Sure.
Uh, so, what is the shape of a gravitational wave?
A shape of a gravitational wave. So, as I said, a gravitational wave is quadrupolar, which means that It is three-dimensional, right? It's going to stretch the space-time fabric around you. It is a little hard to visualize,
Right.
but when you see demonstrations, what people do is they have a black cloth. The easiest way for you to visualize is if I drop a stone in a lake, it's going to create ripples. And that ripple, you can describe it in the X and Y direction, right? Suppose the same ripple is traveling across 360 degrees across the object, not just confined to the surface of the water, but space as well as water. Then it's going to be a ripple across, and it will be a stretch and squeeze. So if a gravitational wave is going to cross through Earth, it's going to wobble the Earth. It is like a ball that gets an impact, right?
Right.
A ball that gets an impact on a wall. If you were to observe slow motion of a ball getting an impact on the wall, the ball actually stretches in one direction and squeezes in the direction where it gets an impact. So it's a stretch and squeeze effect. So that
Right.
is exactly what a gravitational wave would do to an object. It's quadrupolar in nature, so it's a little difficult to visualize because we
Right.
are used to looking at waves in two-dimensional on our book, and what you see is it is confined to a particular surface. So it's that's why we call gravitational wave detectors as antenna. If you see in the early proposals, they didn't call it a telescope because they called it an antenna, because it's like the waves that are around you and you want to detect those waves with an antenna. The same, if you build you must have heard talks about radio wave antennas, radio
Right.
astronomy, radio antennas. So those LIGO is similar to that. So it's not like a telescope, but it's more of an antenna. So
Right.
you are trying to detect the waves around you by looking at the physical effect of the gravitational wave. So how it deforms the object is the way that it manifests itself.
Yeah, I think what you said was the best thing, stretch and squeeze. It's
Yeah.
changing the shape. Yeah. So,
It's a
uh,
wobble. It's a wobble. That's what
wobble,
it's a
right.
wobble.
And like you described, the technology of building this is going to be very, very challenging. And, one of the questions is, why are the mirrors isolated?
So, as I said in the first picture, we drew a ring of test masses, right? So, if you want to look at the effect of a gravitational wave on any object, if you want to measure the wobble, your object should not wobble for anything else that is there around it, right?
Right.
So, that means that if the mirror is going to feel the impact of the gravitational wave, it should not feel the impact of anything else that is around it. And the way we achieve it is by suspending the mirrors. So this gets a little technical as to why we suspend, but you can do a simple experiment at home, and then it should give you an idea as to why we suspend. So if you take a simple pendulum, say you hang a pendulum, and then the pendulum moves, right? The pendulum has a resonance frequency, means a frequency at which it has the maximum amplitude, right? So if I take my suspension point of this pendulum, and I'm going to move this at the pendulum's resonance frequency, or when the amplitude is the maximum, I will trigger it to move at the maximum amplitude. But now, if I move it very fast, let's say 1,000 times faster
Right.
than its resonance frequency, if you do this experiment, you'll see that the pendulum is barely moving, even though the suspension point is moving very fast. And this is what we call, this is exactly the principle, the fundamental principle that we use behind suspending the test masses. We know what we do is we design this pendulum so that its resonance frequency is much lower than the detection band of the gravitational wave. So the gravitational wave that we detect is of the order of a few hundred hertz to a few kilohertz. And if I design my pendulum to have a suspension frequency close to few hertz, then when I have 100 hertz frequency that's coming and trying to move it, I will be able to, this is still a test, this is still going to be isolated to everything that is around it for the higher frequencies except for the gravitational wave. So the suspension point motion at 100 times faster than its resonance frequency creates what we call a freely falling test mass that is not subject to anything else around it.
Right.
So you can do this simple experiment at home. Take an object, suspend it, move it slowly. You will see that it is moving with a very large amplitude. And then you move this really very fast. You'll see it is stuck there. It doesn't move. So that's the principle behind suspending these mirrors. That's how we create a freely falling test mass.
So can you explain? I mean, you discussed it, but how does LIGO contribute to astronomy research?
So you must have heard about different telescopes, right? Different telescopes, they create images of the sky um, from in different parts of the electromagnetic spectrum. So if you look in the X-ray spectrum, the sky will look like something different from what you look in the gamma ray spectrum, because every object emits electromagnetic waves in different parts of the spectrum. So similarly, we have the objects that emit gravitational waves are really compact objects, like black holes and neutron stars, which are really, really heavy. And black holes, they don't emit in the electromagnetic wave spectrum. So now if I want to look at the sky and map where these black holes exist, it's not possible for me to have a telescope built in the electromagnetic wave spectrum to look at the map of black holes. So I need to create a sky map. And the way I create a sky map is by looking for waves that these compact objects emit when they move around. And when these compact objects move around, they produce gravitational waves. So there are different types of gravitational waves. The ones that we detect are called compact binary mergers. Means there are two heavy objects that move around and then merge. And those are the gravitational wave signals we've detected so far. There are also other sources. For example, the background that we have from the Big Bang that happened, the gravitational wave that happened from the Big Bang, is also something that we are looking for to detect with gravity, but we've not made a detection of.
Right. Mostly it's been the mergers
of gravitational waves.
Mostly the mergers of black holes.
Yeah, there are also objects, these compact objects, if they're not perfectly symmetrical, if they're asymmetrical, also, they will create gravitational waves.
Yeah.
So
Thank
if they're
you.
going around and they're asymmetrical, they're going to create gravitational waves. And that's the different class of gravitational waves, different types of sources. So that's a different source. So we want to create a map of the sky with these compact objects which don't leave a trace in the electromagnetic spectrum.
Right. So where is the LIGO India going to be located? And also some students are asking, can we visit it? So I know it's not yet been built, but when is it projected to be built, and would visitors be allowed then?
The LIGO India detector will be in Hingoli, Maharashtra, which is about 10 hours from Pune. If you know where Pune is, you go inland, it's about 10 hours by road. And right now, we have a fenced space with a site office where the detector is going to be built. So as I said earlier, it is very difficult to build a 4 kilometer straight arm, because of the curvature of the earth. You go 4 kilometers, you have to dig through earth to make it straight, and light travels in straight lines, and we use light to bounce back across 4 kilometers in a straight line. So what we do is, if we want to build 4 kilometer arms on both straight arms on both sides, you have to dig through a bit of earth to make it flat on the surface of the earth. So the moving of earth will happen very soon, hopefully by the end, in a few months, we should be able to move earth. And so as you can see, most of the action of the detector happens in the heart, as I showed you, where the beam splitter is, right? So as we keep building the arms, we will integrate the detector in the mid station, as we call it. So detector will start coming up in the mid station. And as I said, it's vacuum, right? 4 kilometers of vacuum on both sides. So the vacuum work will go on for 3 years, but then at the end of 5 years, we should have a functioning detector. So the project deadline is 2030.
Okay.
And we hope we'll have the detector by then.
So thank you. And are there any student internship or summer school opportunities in LIGO,
So,
or in more generally at IUCAA? Also, you can talk about.
so in general, there's no dedicated program for LIGO in India summer school as such, but we've been catering to what is called the LIGO Surf program, wherein some of the students have been able to visit the observatories and the laboratories at Caltech. But this program is for students in their second year. If they finish the first year of masters, it happens in the second year of masters. Because as you see, the collaboration is wide. So right now, the opportunity to go visit the collaboration labs in other countries have also opened up. So if you go to the LIGO India webpage, you'll find opportunities, and in there is an encouragement for students to make their application for enrolling in these programs. Um, so then there is a shortlisting, and few students get to go every year. Apart from that, we also organize workshops in IUCAA. So for the data analysis, we have open data workshops that happen from time to time. You should be able to see that in the IUCAA events page. And it's a recent thing that we started for people interested in instrument science. So starting last year, Ayuka has been doing an instrument science workshop. It's again targeted for students in the master's level. And they get to spend a few weeks spending time in our laboratories here, learning the basics of gravitational wave instrument science. So now that we are in the project mode, I think we'll have more dedicated summer schools and more dedicated workshops to bring in to attract more students
So,
to LIGO. Yeah.
since most of the attendees right now are school students, I would also like to share. I think IUCAA has visits for school students, right? And sometimes workshops for school students.
Yes, so Ayuka does this through Ayuka has a long legacy of doing this for school students from time to time. So people can approach our science popularization team, and you can drop an email saying you would like to visit, and you can visit Ayuka. I think it's mostly happens on Saturdays, but they do accommodate during the weekdays if that's what the group prefers, depending on the size of the group and what resources are necessary.
Right.
We do have an open house every Science Day, which is the last day of February. And we have an open house in Ayuka as well. So we get a footfall of more than nearly 7,000 to 10,000 in
Mm.
one day in Ayuka. So that's where we see most of the school students, because it's open house and they get to see everything that's happening in Ayuka. So
So,
you're more than welcome to come and
right.
visit us.
So the last question I'll ask you is, since we are celebrating Women in Engineering Day, have you as a woman scientist and engineer faced any challenges along the way, or for you, has it been reasonably smooth?
So the initial days, there is always this mentality. In general, you find a lot of women in astronomy. The only space where you find few women is when things get hands-on.
Right,
And even in physics, for that matter, you see people when it gets to hands-on, when you want to get your hands dirty, you see the numbers declining.
right,
So for me, it was a challenge in that aspect, because there is always few women in the room,
Right.
every step of the way.
Right.
So when I did my master's, I was the only female. We were two female students among 28 other boys in the class.
Right.
And I was the only female PhD student in my whole group at that time. Uh,
Right.
but but dynamics have changed now. People are more inclusive, and there is, if you have the grit, I think you will be able to. There's nothing that will stop you.
Right.
Um, uh, Always there are many mentors now than there were before. There were very few females in the community, in the STEM community back then, but now you see the population is increasing, and that's a good sign.
Right.
Um, a- and IUCAA has always, I think, 50%, it's always women PhD students in IUCAA, almost 50% all the time. But where we lack is, where I've seen the dip is when it comes to hands-on, you see the numbers dropping. Uh,
Right.
and I think students should be more motivated and not be intimidated by what comes to you, but be motivated, self-motivated as to what you want to do at the end of the day, not by what others say.
Right. Yeah, thank you, because you gave us the field for not just astronomy and how to study objects in the sky, but how these detectors and instrumentation, how difficult it is to build them, and how sensitive they need to be to actually get observations. So I hope students have got the feel of it, and you gave a glimpse into how difficult it will be to build it. And from all of us, good luck to LIGO, and we look forward to great results from LIGO India sometime, in the next, after 5 years. And
Yes, it's a long road ahead,
it's a long road. Yeah.
but a
Thank
very
you again
fun
for
one.
joining us. And,
Yes.
students had a lot of questions. It's a very different kind of topic. So thank you again for joining us. It was a great experience for them to hear you and hear about all the LIGO and gravitational wave astronomy. Thank
Thank
you
you
for
for
joining
hosting
us.
me. Good luck, everyone.
Thank you.